it is.
Oh, yeah. Sorry. Oh, you're okay.
Once you and lost it.
Where were they?
One was in Riverside, and the other two were like I've been there like
Yeah, it's pretty like straightforward. They're just moving variants around. Like, it's pretty much what the map that we did on this range.
yeah, oh really? Yeah, so
Yeah, it like looks difficult, but honestly, like,
oh yeah.
It's okay. Like, yeah, me too. I think I'm just going to class. Yeah.
I need to Wendy to walk upstairs. So in this lab last week, how can I make that up? If I can make it up.
Last week was a computer one, right? Am I remembering wrong?
I'm not really sure.
I know, I was like,
No, last week was this one,
I was
right?
like,
Yeah, the magnesium.
Okay, yeah, we can make this up. Do you have lab, when you have lab normally?
I'd say.
Do you want to make this up next week and Tuesday or something?
Yeah.
Okay, yeah, you can take that one.
Thank
and
you.
look at it.
Awesome. Thank you.
but like Carter stuff is like. Google's estimate, not actual traffic. Like I was like, this is
All right, let's get started. Actually, before we dive in, I'll just make kind of a quick announcement. So I don't know if maybe a few of you made it to Club Fair yesterday. It was kind of at a weird time. It was at like 4 to 6. But I just wanted to advertise Earth Club, aka I've hijacked it as Science Outreach Club, aka I'm not the official advisor though, for technical reasons. But anyways, I wanted to pimp it out because I want to try to do some more outreach events probably in the community. So if you're interested, you can just contact me. So outreach events. Since people are reminding me and I'm getting reminded because past students are asking for recommendation. And so yes, we should try to put some events on the calendar. And that's always good for essays, right? So you can talk about that, yes, I served my community, blah, 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 all that good stuff. So just talk to me if you're interested, and then I'll keep you in the loop. Like I said, we'll try to get some events going. Anyways, let's go back to gases. And so now we're going to put our lab into context, kind of what the heck we were doing. And this is pretty similar, the setup, except they have their tube kind of different here. So I don't know where they're collecting their gas necessarily, but let's talk about our setup. So it's pretty similar to this. And so, right, we had our eudometer tube in here and our beaker of water. And so, right, kind of, again, thinking now our water is kind of acting like our manometer, just like our mercury one. And then the trick with your lab is, right, we started with the whole thing filled with H2O. And so then the idea, and kind of where the math comes in, because, right, last week when we did this lab, I think we probably just mindlessly, right, followed the directions. Okay, it tells me to take this number minus this number. But let's kind of think back, well, why was it telling us to do those? What were we doing? And so, okay, we have our atmospheric pressure, right, beating down on our water there. So when our hydrogen is filling up, right, so then gas was forming. You all saw that I don't know how to draw H2 gas since it's colorless, but right, okay, so then our H2 gas is expanding, and so we have to think about what it's working against, right? So it's working against that atmospheric pressure, and so that's why your calculation, so now I'm just going to have our calcs from lab, and so that's why you started with, right, the atmospheric pressure. So it said, okay, take this number, and then it told you to do some subtraction. And so let's kind of look at what this is getting at here in our notes and where we made the corrections. And so part of the confounding factor is, so yes, right, we're generating H2 and that has this pressure, but we have to account for the partial pressure of water. And so we're kind of getting to this in this chapter, but right, basically we're going to see, or we kind of saw in lab, that right, there's some sort of equilibrium. So even though it's not at boiling, and you all probably know that, right, you can sit out a cup of water and then over time it'll start evaporating eventually to nothing. And so that's because, right, again, even though it's not at the boiling point, there's still some amount of water vapor, water molecules that are escaping. And so that's the pressure that we calculated, right? So it's based off of the temperature. I remember it was 17 millimeters of mercury. Don't quote me on that. Something like that. But right, we did our correction. So minus vapor pressure of H2O, right? So that's why, again, in the lab manual, it just told us, okay, subtract this. Okay, we did that correction. And then the other correction that we did is that it told you, right, to subtract the height of your water column. And so that's because we needed to account for whatever that it didn't push out, right, all the way. So basically, like, yes, and we didn't want this to happen, though, because then we wouldn't be able to measure it. But, right, again, the idea being if you had pushed down the entire water column, then, right, that would be equal to our atmospheric pressure. So you would have, right, pushed all that through. And so if you failed to, so kind of H2O left, which again, right, we wanted something to measure, but okay, that's telling us, yes, we didn't push down this much water, and then obviously, right, you made that correction based off of the density of water, and so then minus the height of the water column, again, right, so that's correcting for what you did not push down for your atmospheric pressure. So does that kind of make sense where the formulas came from? So I don't want to just have like magical formulas that came from the air, right? So now we can see, okay, that's why we did those calculations. And so obviously, right, this is a technique that is used to collect gas and quantify it. And then of course, right, you just have to have some sort of manometer or something so you can take your difference in pressure and figure out how much gas. And so continuing on with kind of our vapor pressure idea, so we saw this chart again in our lab manual, so it's just telling us, again, pressure related to temperature, and then note the boiling point of water, so we should know that as 100 degrees Celsius. And then again, right, it's defined as the normal boiling point since the pressure is 760. So now we can spell that out if we need to, right, defined as normal boiling point. And again, that's just when the vapor pressure is equal to 1 atm. And so that's defined as our boiling point then of a substance. All right, so let's look at our other bits here. I forgot to pull up my notes. Reference. And so now we want to correlate our temperature and velocity. And so we have our kinetic energy of our gas molecules depends on the average mass and velocity. And so people were asking me questions about this. And so we have, right, some of our formulas. So we can start with our kinetic energy is equal to 1/2 mv squared. And again, right, this is just our average kinetic energy. And so it mentions that gases in the same container obviously have the same temperature. And so then they have the same, again, average kinetic energy. Oops, sorry. But we'll look at the distribution of that. And so then if we have different masses, then of course the only way for them to have the same kinetic energy is to have different average velocities. Again, right, kinetic energy 1/2 mv squared, so that makes sense. And so you can probably derive this from the formula, but right, you can tell, okay, well now, again, if they have the same average kinetic energy, if we have a smaller mass, then it's going to have a faster velocity. And so that's what's stated here. But then we've already talked about this, right, in the practical aspects of like concerning hydrogen, fuel, and some of those challenges. So some of you have already kind of brought that up and recognized that as kind of an issue, that you have these small particles of hydrogen. And so they're moving at a faster velocity. They can also escape faster, which we'll get into. And so right now we're just talking about the physical challenges of trying to handle these different substances. All right, so back to the math though. And so then we're given our formula here. And so the only problem is we need to look at our units on this one. And so our R is actually going to be our energy constant. So 8.314 joules mole Kelvin now, since we're looking at kinetic energy relationships. And so then the other thing to note, so of course velocity is in meters per second, that's pretty standard. But then probably put a star by this one. So the only difference now, again, thinking back to your units, okay, joules. And so joules is related to kilogram, right? Kilogram meter squared over second squared. But that means that our mass needs to be in kilograms. And so, right, normally we're given our molar mass in grams per mole, so you'll just have to move the decimal over, right, to put it in kilograms. So that's not normally how we express it, but again, we'll do some practice there. All right, so let's look at our graph so we can just kind of look at what we were just kind of saying visually. And so just kind of mentally start adding up their weights, right? So O2, well, that's 32 grams per mole. I guess I should have put 0.032, right, if we want to start thinking kilograms. Either way. And so again, right, kinetic energy 1/2 mv squared. And so note that something that has a higher molecular weight, right, has a tighter distribution. And that's only because, right, it doesn't have molecules that are moving as fast. Because now this is just, right, our distribution snapshot. So this is saying, okay, we can just take all our molecules, right, they're all moving around randomly, maybe some are switching direction, have just collided, blah, blah, blah. And we could just take the distribution of all those speeds. This is what we would get. And so again, right, something with a higher mass has a smaller distribution, since again, right, this is going to be like your max speed over here. Versus, so obviously H2 is our lightest element. And so it has the largest distribution, right? Because again, at one point, maybe you have a molecule that's not moving, right? It just finished colliding. So it has a velocity of 0 before it turns around. But it also is showing, right, we can also find one that's the fastest, again, related to that kinetic energy. So one could have a really fast velocity. And so again, right, your average velocity is going to be there for a molecule, right there for O2. And so we can figure out, right, our average velocity. But again, we're just saying this is our Gaussian distribution then of all our molecules cycling around. Does that make sense? What's shown here on the graph? So again, just kind of arrange them in their masses. So 28, 18, 4, 2. So again, just kind of seeing that distribution. And so again, right, we're looking at our average. And so another way that we can express kinetic energy is, of course, by this formula. So now this is just relating our temperature to kinetic energy. And so again, right, they just have a direct relationship. So obviously as temperature increases, so does our kinetic energy. And again, note the units for this one. If we're talking about energy, then we need our energy constant. And so now we just have rederived our formula from before. Oops, sorry. So again, getting us to this formula. So then, right, our Na here is just the molar mass, so they just use a different symbol. And so again, right, we're just seeing this relationship. So as temperature increases, average velocity increases, right? Again, we could be thinking, okay, kinetic energy is obviously also increasing. And so now we'll look at, again, another distribution. So pretty similar to the concept we saw before. So again, as our temperature of our gas increases, so then we're going to have a wider shift. So again, right, you can kind of have this greater potential for higher velocities with these high temperatures. And so that's kind of shown here, right, in our 2000 Kelvin, saying, okay, again, instantaneously, we can have a molecule that's moving super fast versus, right, 273 Kelvin, where there's less, again, variability. So then we're saying, right, our fastest ones are only moving around 1,000 meters per second or so. So again, our distribution spreads out. And again, right, so then we could quantify this. You could just kind of, visually do it or think about using your calculus skills. But right, so now we're seeing, okay, yes, so that means more of them are moving faster, again, as our temperature increases. All right, so see if we can do our practice problem. So calculate our root mean square velocity of oxygen molecules, and of course diatomic oxygen at 25 degrees Celsius. And then I'll scroll back up to the formula. I have to look at the book. And try to pull it up in the meantime. So do we have answers or? Yeah, so I'm just kind of walking through. So, right, we started with this formula. So again, right, it's kind of presented in two different ways, but the same thing. So, right, it's just wanting our molar mass in kilograms per mole. We have our R, which is just our other gas constant, our energy one. And then T. Don't forget T has to be in Kelvin for every calculation that you do, essentially. 8.314. And then that gives us about 298 Kelvin over 0.032. So that should have been the setup. And then let me pull up the calculator. So then I'll just start. So 3 times 8.314 times 298 divided by 0.032 and then square root. And so then I got 481, and then right, we're in meters per second, again matching up with our joules. Do other people get this? Yes, no.
So wait, where did the 0.032 come from?
So this was just expressing, because right, normally we would say, okay, well, the molecular weight of oxygen is 32 grams per mole, right? But then we said, okay, we have to use kilograms, so we just move our decimal over and convert to kilograms per mole. That's where we get the 0.032. Yeah, and I really think this is like the trickiest part, just because we never do this in chemistry. We're always in grams, so the little kilogram feels weird. And then probably just 2 sig figs here, so I'll round it to 480 meters per second. All right, let's see. And so then looking kind of at the last bits of our chapter, so now we have our mean free path. And so again, all this is to say is that, right, molecules in a gas travel in straight lines until they collide, right, either again with another molecule or the container. And so then you could calculate what's called your average distance a molecule travels, right, between collisions. And so that is just considered its mean free path. And so, okay, well, let's think about what we're saying. And, well, now this makes sense. So it says the mean free path decreases as the pressure increases. And, well, this makes sense, right? So, of course, as pressure increases, we're already saying that more collisions are occurring, right? That's literally why the pressure increases. So then, yes, if there are going to be more collisions, then that would make sense that our mean free path decreases. And so then, again, continuing, these are, again, just kind of putting all those little concepts together. You probably have thought about this, but now we're just putting it all together. And so again, we mentioned diffusion and effusion. And so we have the process of collection of molecules spreading out from a high concentration to low is called diffusion. And so, right, that's just like the perfume, right? You spray some perfume and then it starts filling up the room. And then, again, thinking back to hydrogen transportation and storage issues, So the process by which molecules escape through a small hole is called effusion. And so again, right, you could think about that for your balloons too, right? Those helium balloons are nice, but they might leak out faster. Unless you, of course, like, now they have some pretty intense seals on some of those balloons, but if you were to just compare a helium versus a heavier gas balloon, right, the helium one would shrink. If you've ever done my demos with me out to the schools, so I do a chemistry magic show, and if you prepare too early, you can really see the difference. So I blow up these balloons of hydrogen and oxygen, just like I did for y'all in class. And if they're prepped like the night before, usually the stockroom tries to go for the same size, and then the next morning my H2 one has always shrunk more than the O2 one. Usually the O2 looks just fine. Anyways, those just practical observations. And so again, we kind of danced around this, but now we're just re-emphasizing it. So again, these rates are related to those root mean square velocities. So again, obviously, right, we're seeing those smaller particles are moving faster, and so they can escape. And again, right, so for gases at the same temperature, this means our gas movement is inversely proportional to the root mean square of its molar mass. So again, right, we're just saying that as our mass gets lower, our speed gets faster. So there's our inverse proportion. And we'll see the math, which can be tricky just because of the inverseness. But again, we'll look at that. And so now we have the math relationship. And so this is what I mean by the formula could be a little funky. And so again, we're looking at this inverse relationship. So then we have the rate of A over the rate of B is equal to the square root of the difference, right, of our masses. So our mass of B over A. So I'm just going to highlight A so we can see, right, if A is on top on one side, it has to be on the bottom on the other. So that's, I think, the tricky part about this formula. All right, let's look at the little caveats. So we'll just talk about real gases, but then in practice, we're not going to do anything with real gases, but you should at least kind of know the differences and how to calculate them if you were interested, but again, usually not relevant. So let's look. And so again, right, we've been making a lot of assumptions. So that goes back to, right, what we defined as our kinetic molecular theory of gases, right? So the problem, again, with this is we made a lot of assumptions, right? We had initially said that there's no intermolecular forces, right? They're just all moving in straight lines, perfectly elastic collisions. And so, of course, that's not perfectly true. And so, of course, it mentions, right, the most deviations occur at high pressure or low temperature. And again, we'll look at those. And so, again, breaking down the assumptions that were kind of erroneous. So, again, we're assuming no attractions when we just talk about this kinetic molecular theory. And again, right, we assume that they don't really take up appreciable space. So, again, right, we said we're going to treat the identity of all the atoms the same. And again, it basically holds true. But of course, and we've already kind of somewhat talked about this, right? So at low temperatures and high pressures, these assumptions are not valid. And many of you, right, started bringing up terms like it's going to be a liquid, it's going to condense. So yes, right, you're recognizing that they are intermolecular forces, you know how they behave, you understand that yes, they will undergo a change in matter. And so then, right, we can also appreciate that, okay, yesterday, or not yesterday, but on Tuesday, we said that at STP, right, 1 mole was 22.4 liters for any gas, right? And again, we'll still make our assumption for our calculations, but I just want you to appreciate that yes, there's like small variations, and that's going to be based off of, you know, their size, their attractiveness. And so again, right, we can compare our ideal gas versus, so chlorine, right, just a little bit less. CO2 is pretty on par. You know, ammonia, pretty ideal, again, under these situations. But it's just interesting to see, yes, there is, right, a small amount of deviation. But again, still basically 22.4. So that's why we use it. But yes, there are differences in real life, just not that appreciable for our purposes. And so again, we kind of already thought about this, but let's just again re-put it together. And so at low pressures, our molar volume of argon is basically an ideal gas. But of course, as our pressure increases, then our molar volume of argon becomes greater. And so I think, again, you had already recognized that with some of our Boyle's law limitations. But, right, again, eventually at higher pressures, the atoms at some point occupy physical space. So, yeah, we cannot compress them any further. So in this case, right, the actual volume is greater. And so again, right, our real molecules take up space, so our molar volume of real gas is again larger than predicted. And so we can see just an example of where that deviation starts to occur. And again, right, you can bring up those terms, condensing, thinking back to, right, liquid nitrogen. So again, right, it just depends on the pressure valve that your big liquid nitrogen tank is set up. So I think it's usually 231 psi is considered high pressure, and that'll give you the gas. And then I want to say 22 is where the liquid comes in. So it's just whatever pressure your valve is set at. But, right, it's still a liquid. And so then, again, we're not going to do this in this class. You don't have to panic. Just appreciate that, yes, modifications exist. And if you were doing some research thing or whatever where you did need to do the calculation, the correction, I want you to be aware that, yes, there is a correction. You can correct for it. And so again, Johannes van der Waals then modified our ideal gas equation. And so this corrects for our volume of gas particles. And so you would, of course, have to find this van der Waals constant. So, right, that's gas dependent. So, again, that gets into very specific scenarios. But then again, right, you can just see that you can make this correction. So, again, that's all that we want to take away, that, yes, you can make a correction if you needed to. We're not going to be doing that in this class. And so now let's look at our intermolecular attractions, or again, just kind of think about that. And so at these high temperatures, the pressure of a gas is nearly identical to that of an ideal gas. And again, kind of think about why, right? At high temperatures, your gas particles are going to be far enough anyway, so even if there are intermolecular forces, right, it's not really that appreciable. But then, of course, right, as we get to lower temperatures, they start getting closer together. Well, now those intermolecular forces will come into play. And so, right, it says the pressure of gases is usually less than that of an ideal gas. And so, again, at those lower temperatures, now they're just physically closer. more time interacting with each other versus any other walls or anything. And so again, right, those intermolecular forces start making our molecules interact. And so of course this makes the pressure lower. And so as you might expect, then there's another correction. Again, we're not doing that, just appreciating our correction. So again, you would have to look up another van der Waals constant. So right, look that up, and then you can make your correction there. And so then, yay, if you really, really needed to be super precise, again, for whatever reason, I personally don't know what the application would be. This isn't quite my area of specialty, but right, again, you have that formula there if you ever find yourself needing it. And so again, we can just kind of appreciate the deviation, and then, right, obviously there's going to be more deviation. So why do you think water has such a weird deviation? What can you expect?
Because of its polarity and the amount of intermolecular forces.
Yeah, so it's very polar, and then we're still kind of getting to intermolecular forces. But yeah, basically strong interactions, intermolecular forces. We could use the term hydrogen bonding, which I don't think we properly have introduced in this class, but we'll get to. Or even just the fact that water has a high boiling point. So that's the other thing that we'll kind of talk about. So water is pretty special, right? It's a very light molecule of only 18 grams per mole, obviously, but then has a super high boiling point, again, for its molecular weight. And so that's, again, what's leading to a lot of deviation from its ideal gas behavior. And, I mean, pretty interesting. They all kind of deviate. But I like the water deviating so low. And, of course, helium, a little higher. Again, lighter molecules. All right, let's see. Let's do one of the velocity problems from your homework. I can pull it up. Oops. Uh-oh. All right. I'm not seeing the problem that I was thinking of, but let's try another one while I try to find what I want to do. Have you tried these mixture ones? Sometimes these go funky. So this is number 5 from your homework. So let's practice our partial pressure while I try to find our relative velocity question that I wanted to do. So we have a mixture of 5.25 grams of CO and 8.43 grams of CO2 that have a total pressure of 1.75 atm. So what are the partial pressures? So how's this one coming? What do we have to do for this one, kind of? Instead of asking. Yeah, so let's find moles of each. And so, right, eventually we're trying to get to the mole fraction is where we're getting at, right? So we want eventually mole fraction. But of course, right, that means we have to find, well, how many moles of CO do we have? How many moles of CO2? Because, right, all we care about is the N total moles for our gas. And then we can figure out, right, our mole fraction to get our partial pressure. And so then, help me with that. So CO, 5.25 grams. What's our molecular weight? 28.01. And so then how many moles do we get? 0.1874. Of CO. And then, right, just repeat for CO2. So 8.43 grams over, what's our molecular weight?
44 grams.
44 grams per mole. And so then how many moles of CO2 do we get?
0.916 mole.
0.916. And so right now we can just figure out mole fraction of each. So right, kind of recall what the mole fraction formula is if you need to. So mole fraction of anything, right, of A is just going to be moles of whatever you're looking at over total moles. And so now let's do that for CO first. Although it doesn't really matter, right, because then we could subtract or whatever. So then we can do, so 0.1874 over 0.1916 plus our moles. So then we get our mole fraction, or right, our percentage of about 49%. So 0.4944, or I guess round it to 45. So 49.45%. And so we could either, right, calculate it for the other one, or we could just subtract. So, right, then we can multiply this percentage by our total pressure. And so now that's our pressure of CO. Times 1.75 ATM. So now that's 0.865 ATM for CO. And so then, right, we could just subtract if we wanted to take the easy route here. So 1.75 minus. So then, right, this has to be the remaining amount for CO2 then. Obviously, you could also have calculated the mole fraction, and then would give you a similar answer with rounding. So 0.88. I got 5 ATM. I think the key has 884, but again, right, a little bit of rounding discrepancies there. Questions on that one? All right, let's look at the type of problem that I had in mind. I thought it was on your homework for some reason, but. Start a new page. And so now this is asking for, I apologize, I didn't copy it very well. It says, what's the molar mass of an unknown gas if the gas diffuses through a pinhole into a vacuum at a rate of 2 milliliters per minute? And then we're comparing it to H2. So assume, obviously, that the rate of diffusion is proportional. And let me get the formula for you to help. So, right, we need this formula. I'll just see if I can copy. Oh, that didn't work. So I'll just recopy it, where again our rate of A over our rate of B is equal to the square root of our mass of B over A. So try that out. Notice, right, units cancel, so they could both be in grams. That would be okay. You don't have to do kilograms. Sorry. Oh, and then, yeah, if you were looking for this in the textbook, I think it kind of starts on page 448 and kind of goes over to 452, 448, sorry. So that's what I was saying, that it doesn't actually matter anymore, because now, right, you're dividing. So they could be in kilograms over kilograms will be the same, or grams over the grams. So it doesn't matter. So if you want to put them back in the grams like we're used to, that's fine. Yeah. So I'll start going over it. So again, right, the trickiest part is our setup. So just, right, don't do anything funky. So we have, okay, H2, right, maybe I want to call this A. And then, of course, our mass of H2, 4 grams per mole. Again, right, units cancel, so we can go back. And so, again, don't screw up these setups. So, okay, if my A is on top, so 10 milliliters, or excuse me, 11 milliliters over minute, and then B, our unknown, so 2 milliliters per minute, is equal to, right, our square root, or we could also square this if that's easier. So then our mass of our unknown squared over 4 squared, right? Or, sorry, the mass of H2 is not 4. 2. I don't know why I said 4. Sorry, 2. 2 grams per mole, my bad. Too excited. It doesn't matter, right? So you could have flipped this, so you could have had 2 on top, 11 on bottom, and then 2 would have to be on top, right? So as long as you flipped everything. And so now we can solve. So now I'm just going to plug it in. So 11 times 2 squared. So that's where I got the 4. I got it overexcited. And then divided by, I feel like I did something wrong.
Wouldn't you just like to square the rate? And then we can
Oh,
the mass?
yeah, I should have squared both sides. You're right. So then, yeah, 121, sorry, milliliters over 4 is equal to, thank you, 4 over this mass B squared. Sorry, can't do math today. All right, one more time. So 121 times 4 divided by 4, and then second square root. I don't know what I'm doing today.
Only the one side should be
Yeah.
squared.
Yeah, I totally screwed this math up for some reason. All right. I don't know what I'm doing, obviously. One more time. So, right, square this. So then this goes away. This should be 2. All right, does that sound better? I apologize for screwing up the math so badly today. All right, 121, one more time, times 2 divided by 4. And so do we get our mass of 60?
60.5.
So 60.5. Again, make sure I didn't screw up anything else on that one. Sorry, I was just double checking.
You said it could be either way?
No, you wouldn't change your answer, right? So if you flipped it the other way, yeah, without screwing up the algebra this time. Yeah, so it wouldn't matter because it's just cross multiplication. But yeah, I apologize for the massive squaring screw up. So yeah, square both sides, so that would obviously have gotten rid of that, square that, leave you the masses. So I could rewrite it as well since I screwed up so royally today. Equals mass of B over mass of A. So that was the other form. All right. Questions on that one? All right, so that I think is good. So I'll hand out our quiz, and then obviously, right, you can take your break. And if you need it by email, just let me know. I'll leave the stream running for a second in case there are last minute questions. Is it 3 people on there or 2? Oh. Yeah. Just pass it.
I looked at the first page.
You have a paper copy? I'm not. Okay.